Hello folks, this is Jack with another video presentation. It's a quickie this time on De Morgan's theorem. It's kind of in the minimization umbrella, but it's not really used for simplifying. It can be used for simplifying, but sometimes it's used to convert an expression into a different form so that it uses different logic gates. The theme for this session is De Morgan's theorem. De Morgan's theorem states that these two Boolean expressions are exactly the same. Now let's look at what the gates these expressions represent. The one on the left is a 2-input NAND gate, and that is equal to a 2-input OR gate with inputs inverted. Please note that the expression on the right is not a 2-input NOR gate, it's a 2-input OR gate with inputs inverted. If it was a NOR gate, then the bar would extend over all the variables. It doesn't, therefore it's not an OR gate, it's an OR gate with its inputs inverted. So the upshot of this is a NAND gate can be converted into an OR gate with its inputs inverted. And also a NOR gate can be converted into a 2-input AND gate with its inputs inverted. This version of De Morgan's theorem is break the line, change the sign. In terms of functionality, they are identical in terms of functionality. In terms of actual physical gates, they are obviously different. However, if the gates on a circuit board and the user can't see the gates, all the user can see is the input and the output, well, the user will never know what gates are in there. Okay, so in terms of functionality, they are identical. And an easy way to remember De Morgan's theorem is break the line, change the sign. Can you see on the left on both of the expressions? If you break the line where the operator is and or, if you break the line there and change that sign, change the sign from and to or to and. Okay. Right. So De Morgan's theorem states that a 2-input NAND gate is equal to a 2-input OR gate with its inputs inverted. And there you go, there's proof. So any doubt, always truth table it and convince yourself that it's true. They are equal. Also, a 2-input NOR gate is equivalent to, in terms of functionality, a 2-input AND gate with its inputs inverted. Okay, excellent. Now, the use of De Morgan's theorem is that it can be used in terms of simplification when you just want to break the bar. If you have a bar extended over variables, sometimes it's difficult to apply the rules of Boolean algebra, and this allows you to split the bar and kind of apply the rules of Boolean algebra. It can also be used to actually give us some flexibility as engineers to use what we have in the stores. You may not have AND gates in the stores, you may only have NAND gates. So using De Morgan's theorem, we know how to convert our expression from using one particular type of gate to one particular type of gate. So it gives us a flexibility. Right, there is another version of De Morgan's theorem which is works on uncomplemented expressions. For example, the expression on the left is a 2-input AND gate. Now that is actually equivalent to a 2-input NOR gate with its inputs inverted. A 2-input NOR gate with its inputs inverted. Also, a 2-input OR gate is equivalent to a 2-input AND gate with its inputs inverted. Now, this hasn't got the same ring about it as the previous one did. Break the line, change the sign. This one is make the line, so actually extend a line over the variables, change the sign, and or and invert the inputs. Okay. Truth table. 2-input OR gate is equivalent to a 2-input NAND gate with inputs inverted. Two-input AND gate is equivalent to a 2-input NOR gate with inputs inverted. Okay, let's go for this question. Apply De Morgan's theorem to the following expression. We can see that expression there. It's the expression is not A or not B, and C or D knotted. In terms of gates, this is using a 2-input OR gate with inputs inverted, two input OR gate with its inputs inverted, another 2-input OR gate, C and D, and both of those gates have been NANDed together. Now we have to apply De Morgan's theorem in stages here. Apply it to the top bar. So the top bar in the middle of it is the AND gate. So split that into 2 and change the sign. So can you see what I've done there and where I've actually split it? It's that AND operator in the middle of the 2 brackets. I've changed that to an OR operator and split the line just above it. Now we can apply De Morgan's theorem actually again, can't we? Because we can apply it individually to those 2 terms. Break the line, change the sign. There you go. Now on the term on the left we've got a double negative there, and of course double negatives cancel out, so applying De Morgan's theorem we have that is equivalent to the expression above. Okay. I said it was quite brief, and that's really all I wanted to cover in this particular presentation. I will post another presentation shortly on counters, hopefully tomorrow. Thank you very much. Okay, bye.